Something is moving through our solar system the wrong way. Every planet, every asteroid, every comet we have ever tracked orbits in the same direction. That pattern held for 4.5 billion years. Then astronomers caught something moving against all of it. A single object. Wrong angle, wrong direction, wrong everything. We are going to follow where it came from, what threw it off course, and what it is pointing toward, including a hidden mass so large it may rewrite how our solar system was built. If you enjoy this, subscribe and leave a like. It helps more than you know. Brace yourselves. We begin. The alert came in quietly. No alarms. Just a number on a screen that did not belong. A sky survey telescope was doing what it always does, sweeping across billions of miles of dark space, logging the positions of rocks, ice, and debris drifting through the outer solar system. Most of what it finds follows the same ancient choreography. Objects orbiting left to right, tilted at shallow angles, moving in lazy, predictable loops around the sun. The software had catalogued thousands of them. Then it flagged one. The object was moving right to left. That single detail set off a chain of phone calls, cross-checks, and sleepless nights in observatories across 2 continents. Researchers pulled the data again. They checked the instrument calibration. They reran the trajectory math from scratch. Every calculation came back with the same answer. This object was traveling in retrograde, meaning it was orbiting in the opposite direction from virtually everything else in the solar system. To understand why that matters, picture a massive highway with hundreds of thousands of cars all driving the same direction. That is our solar system. Every planet, every known asteroid belt, every comet trail, all of them inherited their direction of travel from the spinning cloud of gas and dust that collapsed to form the sun 4.5 billion years ago. The spin of that original cloud got passed down like a genetic trait. Everything born from it moves the same way. This object was driving the wrong way down that highway at full speed. The detection came from one of the wide field survey programs designed specifically to catch fast-moving or unusual objects in the outer solar system. These systems photograph the same patches of sky repeatedly and use software to track anything that shifts position between images. The object had been moving fast enough to show clear displacement across multiple nights of imaging, which actually helped confirm the trajectory. There was no measurement error. The path was clean, consistent, and deeply wrong by every standard model of how things out there should move. What made it stranger was the angle. Most objects in the outer solar system orbit within a relatively flat band, a zone called the ecliptic plane, which sits like a disk around the sun. Even objects that drift a little above or below that disk stay reasonably close to it. This object was coming in at a steep angle, cutting across the ecliptic like a knife, which is another signature of something that got violently redirected at some point in its history. Gentle gravity does not produce steep retrograde orbits. Something dramatic had to happen to this object. The scientific team published their initial findings with careful language, the way researchers do when they know the data is solid, but the implications are enormous. They confirmed the orbital parameters. They confirmed the retrograde classification. And then they raised the question that has been driving the search ever since. Something sent this object on that path, and whatever did it was powerful enough to flip an orbit entirely. The object itself is estimated to sit somewhere in the range of a large rocky body, big enough to track reliably over multiple observation windows, small enough that it has been drifting through the outer darkness for possibly millions of years without anyone noticing. The fact that we caught it at all is a function of timing and instrument sensitivity that did not exist a decade ago. But catching it raised an immediate follow-up problem. If something out there has the gravitational muscle to do this, where is it? That question is what everything after this builds toward, because the orbit of this object traced backward through time and space, is pointing at something, and scientists are not sure they want to find it. 4.5 billion years ago, our solar system did not exist. In its place sat a slowly rotating cloud of hydrogen gas, helium, dust, and trace amounts of heavier elements scattered by ancient dead stars. That cloud was enormous, stretching across distances that would take light years to cross. And it had a spin, a slow, almost imperceptible rotation that would eventually determine the fate of every single object born from it. When the cloud collapsed under its own gravity, it did what all spinning objects do when they shrink. It spun faster. Think of a figure skater pulling their arms inward during a turn. The rotation accelerates. The cloud flattened into a disk. The center grew dense and hot until nuclear fusion ignited and the sun was born. Everything left over in that disk, the leftover gas and dust and chunks of rock and ice, began sticking together, smashing together, growing into planets, moons, asteroids, and comets. Every single one of them inherited the original spin of that cloud. Every one of them began orbiting in the same direction. This is called prograde motion, and for 4.5 billion years, it held across our entire solar system, with almost no exceptions. The 8 planets all orbit prograde. The asteroid belt orbits prograde. The vast majority of comets and small bodies orbit prograde. Even the dwarf planets follow the rule. The direction of travel that was baked into the raw material of our solar system at the very beginning has been preserved across billions of miles and billions of years. That kind of consistency is not trivial. It is a fingerprint. It tells scientists exactly how the solar system formed and confirms the fundamental models of planetary science that have been refined for over a century. A retrograde orbit punches a hole in that fingerprint. For an object to flip into retrograde, it needs a force applied to it after formation. The original spin cannot produce it. Something external has to reach in and reverse the direction of travel entirely. The energy required to do that to a sizable rocky body is staggering. You cannot nudge an object into retrograde. You have to violently redirect it. There are a handful of mechanisms that can achieve this. A close gravitational encounter with a massive body can swing an object around and spit it out on a reversed path. A collision between 2 objects can dramatically alter trajectories. Or the slow gravitational influence of an unseen massive body applied over millions of years can gradually tilt and twist an orbit until it flips entirely. Each of those explanations carries different implications, and each one requires something that scientists have either struggled to find or have not yet confirmed exists. The 4 billion year rule was never expected to be perfect. Scientists always acknowledged the possibility of rare retrograde objects. A few had even been detected previously, tucked into the far outer solar system, in locations where they could be noted, studied, and filed away. But those objects shared something in common. Their existence could be explained without invoking anything extraordinary. This new object is different in a way that keeps researchers up at night. Its orbit, its angle, its speed, and its trajectory all line up in a pattern that points outward toward a region of space that has been controversial for years. The 4 billion year rule just developed a crack, and whatever made that crack may still be out there. Something created this orbit, and the math keeps circling back to the same suspect. The night the data came in, nobody in the control room expected anything unusual. Sky surveys run on a rhythm of routine. Telescopes sweep preset grids of sky, cameras collect light across millions of pixels, and software chews through the imagery looking for anything that moved between one night and the next. Asteroids, comets, and distant icy bodies all betray themselves by shifting position against the fixed background of stars. The system flags the movers, logs their coordinates, and a human analyst reviews the candidates in order of priority. On this particular night, the automated system flagged a candidate and assigned it a high confidence rating. High confidence means the software is certain it is a real object and not a cosmic ray hit, a satellite streak, or a camera artifact. The analyst pulled up the detection. 3 separate images from 3 separate nights, each showing the object in a slightly different position. The motion was clean and smooth, definitely real. Then, the analyst ran the preliminary orbit calculation. The software returned a result with a negative orbital inclination, a steep one, combined with a direction of travel that placed it firmly in retrograde classification. The analyst checked the input data, assuming a sign error somewhere in the coordinates. There was none. The calculation ran again. Same result. A second analyst was called over. A third. Within an hour, the discovery was flagged for immediate follow-up observation at a second facility on the other side of the planet. Follow-up confirmation in astronomy takes time under normal circumstances. Telescopes are scheduled weeks in advance. Observation windows are allocated carefully, but retrograde detections in the outer solar system carry enough scientific weight to bump the queue. Within 48 hours, a second telescope had the object in its field of view. The measurements matched. The orbit was confirmed. What the data showed was an object traveling at a steep angle across the ecliptic plane, moving in the direction opposite to the sun's rotation, and doing so at a velocity consistent with a highly elliptical orbit. An elliptical orbit means the object swings close to the sun at one end of its path and then flies back out into deep space at the other. This object was on its inbound leg, falling toward the inner solar system from somewhere far beyond Neptune. The trajectory team began the backward calculation immediately. If you know where an object is and how fast it is moving, and in which direction, you can mathematically rewind its position through time and trace where it came from. That calculation placed its origin point somewhere in the extreme outer solar system, well beyond the known population of trans-Neptunian objects, in a region where only a handful of bodies have ever been detected. The calculation also showed something that made the room go quiet. The inbound path, traced backward at a specific angle, pointed toward a consistent region of sky, a region that certain planetary scientists had already been watching, a region that kept coming up in other anomalous detections. The telescope had found one object, but the orbital math was suggesting the object had a story. And that story started somewhere much further out, with a force much bigger than a passing rock. The team issued a preliminary report, careful, measured, technical language throughout, but the last line of the internal summary was blunter than the published version. Something out there kicked this. A retrograde orbit sounds like a simple thing, an object going the wrong way, but the physics behind producing one is anything but simple. Start with the basics. Every object in the solar system carries what physicists call angular momentum. This is the combined product of the object's mass, its speed, and the direction it is spinning or orbiting. Angular momentum is one of the most stubbornly conserved quantities in all of physics. The universe holds on to it ferociously. To change the angular momentum of the object and to flip it into a completely reversed direction, you have to apply an enormous force in exactly the right way. Picture a bowling ball rolling across a smooth floor. To stop it, you need force. To reverse its direction, you need even more. Now imagine that bowling ball is a rocky body dozens of miles across, traveling at tens of thousands of miles per hour through deep space. The amount of energy required to redirect that mass is almost incomprehensible at human scales. There are 3 realistic pathways that produce retrograde orbits in the outer solar system. The first is a gravitational slingshot encounter. When a small object passes close to a massive one, gravity bends its path sharply. If the geometry is right, the small object can be flung outward on a completely new trajectory, sometimes reversed entirely. This is the same physics space agencies use to redirect spacecraft around planets for speed boosts, just operating in the opposite direction, and with vastly more energy. A gravitational slingshot from a planet-sized body could absolutely flip an orbit. The second pathway is a collision. Two objects impacting at high speed and oblique angles can scatter debris in wildly different directions. A glancing blow between two large bodies in the outer solar system could send one fragment into a retrograde path. Scientists take this possibility seriously, though a collision energetic enough to redirect a body of this size would have left other detectable traces. The third pathway is the slow gravitational grind. A massive unseen body orbiting far from the Sun could, over millions of years, gradually pull on smaller objects and tilt their orbits. Given enough time and the right mass, this process, called secular perturbation, can flip an orbit entirely without any dramatic collision or close encounter. The object just gets pulled, degree by degree, until it crosses into retrograde territory. The detected object's orbit rules out the collision pathway almost entirely. Its surface shows no obvious signs of catastrophic fracturing visible at current detection resolution, and its trajectory is too smooth and coherent for something shattered by impact. The slingshot and the slow gravitational grind both remain on the table, and here is where it gets uncomfortable. Both of those explanations require a massive body in the outer solar system, a body large enough to bend trajectories this dramatically, a body that, despite every telescope pointed at the sky, has not been directly seen. The force that created this retrograde orbit is still out there, and the size of the force required to do this puts it well above anything we have already catalogued in that region of space. Numbers in astronomy can feel abstract, but sometimes a single measurement carries more shock than any description. When researchers calculated the full orbital parameters of this object, two specific values stopped the analysis team cold. The first was the orbital inclination, the angle at which the object cuts across the flat disk of the solar system. The second was its velocity relative to the Sun at its current position in space. Most objects in the outer solar system travel at inclinations between 0 and 30 degrees above or below the ecliptic plane. The ecliptic is the flat disk where the planets orbit, and objects that formed naturally in our solar system tend to cluster close to it. The further an object's orbit tilts away from that plane, the harder it is to explain through standard formation models alone. Occasional high inclination objects do exist. Scientists have catalogued them. They sit in the range of 40 to 70 degrees of tilt and usually require some gravitational nudge over a long period of time to explain. This object's inclination is steep enough to place it in a category that currently holds almost no other known members. The orbital path cuts through the ecliptic at an angle that demands explanation. A gradual nudge over millions of years cannot fully account for it. The tilt is too extreme. Then comes the velocity. Objects in the outer solar system move slowly relative to the inner solar system. The further from the Sun, the more leisurely the orbit. This is basic orbital mechanics. Gravity weakens with distance, so objects need less speed to stay in orbit. A body drifting beyond Neptune might travel at only a few miles per second along most of its path. This object is moving faster than that baseline by a margin that researchers have described in their published work as statistically unexpected for its current position. The excess velocity suggests the object received a gravitational boost at some point in the past, an acceleration that pushed it beyond the speed it would carry if it had simply been drifting in the outer solar system undisturbed. That boost had to come from somewhere. A gravitational assist from a known planet could produce some acceleration, but not enough to account for the full velocity excess at this orbital position. The math keeps pointing to a secondary gravitational source, something massive and undetected, that gave this object An additional push during or after the orbital flip now combine both anomalies, a steep inclination well outside the normal range, a velocity higher than the position should allow. Both of these point in the same direction, away from known planetary bodies and toward a region of the outer solar system where the gravitational influence of an undetected mass could produce exactly these signatures. Individually, either anomaly might be explainable through complex multi-body interactions over long time scales, but together, in the same object, they form a pattern. Patterns in orbital mechanics are never coincidental. Every force leaves a signature, and this object is covered in signatures from a force that has no confirmed source. The researchers who first analyzed the speed and angle data wrote in their internal communications that the combination felt, in their words, like a calling card. Something left its fingerprints all over this orbit, and up ahead, those fingerprints start to multiply. Imagine standing at the edge of a cliff and throwing a ball at a spinning wheel. If the wheel catches the ball at exactly the right angle and speed, it does not just stop the ball, it hurls it back in a completely new direction, faster than before. Gravity works the same way. When a small body passes close enough to a massive one, the massive body's gravity curves the small body's path. If the geometry of the encounter is right, the small body gets hurled away on a new trajectory, sometimes dramatically faster, sometimes aimed in a completely reversed direction. Astronomers call this a gravitational slingshot, and it is one of the most powerful orbital mechanics tools known in physics. The leading theory for what happened to this retrograde object involves exactly this kind of encounter, but scaled up to something far beyond a planet flyby. Here is the chain of events the theory proposes. The object began its life in the outer solar system, orbiting in the normal prograde direction, at a steep but not extraordinary inclination. At some point in the past, it drifted close enough to an undetected massive body orbiting deep in the outer solar system to enter a powerful gravitational interaction. The massive body's gravity bent the object's trajectory sharply. As the object swung around it and accelerated, the geometry of the encounter launched it inward on a reversed path, steep, fast, and retrograde. The elegance of this theory is that it requires no collision, no catastrophic impact. The orbit flip happened through pure gravitational mechanics, the same physics that slingshots interplanetary spacecraft around Jupiter or Saturn, just applied at an enormous scale over a fraction of the time that slow secular perturbation would need. The uncomfortable part of the theory is what it demands. A gravitational slingshot powerful enough to do this to a body of this size requires a source mass that planetary scientists estimate would need to sit somewhere between 5 and 10 times the mass of Earth. That is not a stray asteroid. That is a planet, a full-sized planet, undetected, orbiting somewhere in the outer solar system far beyond where any current telescope survey has been able to confirm or rule it out. The region this object's backward trajectory points toward is already a place of intense scientific interest. Several other anomalous outer solar system objects have orbits that cluster in a way that suggests a gravitational influence from that same direction. Researchers have been building the case for a hidden planet in that zone for years, and this new retrograde detection adds a sharp new data point to that argument. What makes this specific slingshot scenario compelling, beyond the math, is the timeline it implies. Based on the current trajectory and working backward, the encounter that produced this orbit may have happened within the last few 100 million years. That is recent by solar system standards. Something massive may have been actively sculpting orbits in the outer solar system in what amounts to the recent past. Wherever that slingshot source is right now, it has had time to move, but it has not had time to disappear, and its gravitational fingerprint is all over this object's path. Every orbit is a record of forces. When astronomers trace an orbit backward through time, They are essentially reading a history of every gravitational interaction that shaped it. And the retrograde object caught by the survey telescope is carrying a very specific history, one that, when traced far enough back, points outward like a finger aimed at a patch of sky that scientists have been nervously circling for over a decade. The backward trajectory calculation is not simple. Orbital mechanics in the outer solar system involve the gravitational pulls of all known massive bodies: the Sun, Neptune, Uranus, the other giant planets, and the known population of trans-Neptunian objects. Researchers feed all of that into models and then mathematically rewind the object's position, accounting for every known influence along the way. When they do that with this object, after stripping away the effects of all known bodies, a residual force remains. A gravitational pull that has no identified source. And the direction of that residual force, the direction it would have to come from to produce this exact orbit, falls within a specific arc of the sky in the outer solar system. That arc is not randomly placed. It overlaps with the predicted location of an undetected planetary body that several independent research teams have been working to confirm for years. The prediction is based on a completely separate set of evidence: a cluster of extreme trans-Neptunian objects whose orbits are all tilted and oriented in a way that cannot be explained by known gravitational sources. Those orbits are bunched together when they should be randomly distributed, and the only explanation that survives statistical scrutiny is a massive body shepherding them from a fixed position far out in space. The retrograde object now adds a new line of evidence pointing to the same location. A second independent data source using entirely different orbital math, arriving at the same region of sky. When two separate pieces of evidence, derived through different methods from different objects, point to the same spot, it is no longer a coincidence. It is a signal. The predicted distance for this hidden mass sits somewhere between 300 and 900 times the distance from Earth to the Sun. At those ranges, even a planet several times larger than Earth would reflect almost no sunlight. The sky surveys currently operating were not designed to detect objects that faint and that slow. The object would move barely a fraction of a degree per year against the background stars, making it almost indistinguishable from a very faint, very distant background galaxy. Almost, the new generation of survey technology is reaching the sensitivity needed to start ruling out or confirming candidates in that range, which is why the pace of this search has accelerated sharply in the last 2 years. The retrograde object is essentially a compass. Its orbit is a directional arrow baked in by whatever gravitational force deflected it, and that arrow is pointing to a specific region of the outer solar system where something massive may be sitting undiscovered. The search is no longer theoretical. Telescopes are pointed at that arc right now, and what they find or fail to find will either confirm the most significant planetary discovery in nearly 2 centuries, or force science to find a different explanation for why this object is moving the wrong way. Either answer changes something fundamental. The hypothesis has a name, and it has been generating arguments in planetary science for nearly a decade. Planet 9. The idea was formally proposed in 2016 by a pair of astronomers at the California Institute of Technology who noticed something deeply strange in the orbital data for a group of extreme outer solar system objects. These objects, called extreme trans-Neptunian objects, all had orbits that were clustered together in a way that defied probability. Their orbits were tilted in the same direction. Their closest approach points to the Sun all fell within the same general arc of space. If you calculated the odds of that clustering happening by random chance, the number came out smaller than 1 in a few thousand. Something was organizing them. The astronomers modeled what kind of mass, placed at what distance and orbital angle, could produce that clustering. The answer was a planet between 5 and 10 times the mass of Earth, orbiting between 250 and 700 times farther from the Sun than Earth, on a highly elliptical path that would take it 10 to 20,000 years to complete one full orbit. That prediction immediately became one of the most debated proposals in modern planetary science. Critics argued that the clustering could be a statistical artifact, a result of observational bias in where and how scientists look for trans-Neptunian objects. If surveys preferentially observe certain parts of the sky, the detections will cluster there, regardless of whether a planet is involved. This criticism has genuine weight, and the Planet 9 proponents have spent years trying to correct for it. The new retrograde object enters this debate with significant force. The reason is that observational bias cannot explain a retrograde orbit. The detection of a retrograde body does not depend on where telescopes are pointed. It depends on the object actually moving in that direction. A camera cannot produce a retrograde signal where none exists, and the backward trajectory of this retrograde object points to the same region of sky that the clustering analysis predicted. That convergence matters enormously. Two completely different phenomena: orbital clustering among small distant objects and a fully reversed retrograde orbit, both pointing to the same location using entirely different mathematical methods, is the kind of double confirmation that causes careful scientists to start updating their probability estimates. Planet 9 has not been confirmed. Scientists are precise about this. A confirmed discovery requires direct observation and multiple independent verifications. The hypothesis remains a hypothesis, but the evidence supporting it keeps accumulating. The retrograde object is the latest addition to a list that has been growing steadily longer since 2016. Each new data point alone might be dismissed. Together, they form an increasingly difficult pattern to wave away. What would Planet 9 actually be, physically? Based on current models, it would sit in a class called an ice giant or super-Earth, a world made largely of water ice, rock, and possibly a thick envelope of gas, larger than Earth, smaller than Neptune. Cold beyond description, lit by a sun that would appear as little more than an extremely bright star. It has been out there, the models say, since the earliest days of the solar system, waiting, silently, for instruments powerful enough to find it. If there is a planet several times larger than Earth in our solar system, why has no one seen it? The answer to that question reveals something humbling about the limits of human observation, even in an age of orbital telescopes and massive sky surveys. Distance is the first problem, and it is enormous. Planet 9, if it exists, orbits at a distance so far from the Sun that the light illuminating it is spread incredibly thin. Sunlight follows an inverse square law. Double the distance from a light source, and the brightness drops to 1/4. At the distances predicted for Planet 9, anywhere from 300 to 900 times the Earth-Sun distance, the reflected sunlight reaching a telescope on Earth would be extraordinarily faint, orders of magnitude fainter than the distant objects astronomers routinely detect. To put that in perspective, Pluto sits at roughly 40 times the Earth-Sun distance and took decades to find with 20th century technology. Planet 9 sits at distances roughly 10 to 20 times further than Pluto. The brightness difference is staggering. The second problem is sky coverage. Space is enormous even within our solar system, and the fraction of the sky that any single telescope can observe on any given night is tiny. Wide-field survey telescopes have improved dramatically in recent years, but covering the entire sky to the depth of sensitivity needed to detect a faint, slow-moving object takes time, coordination, and multiple overlapping surveys. Gaps always remain. Planet 9 also moves extremely slowly against the background stars. An object in a 20,000-year orbit shifts position almost imperceptibly year to year. Traditional asteroid detection relies on objects moving visibly between images taken nights apart. Planet 9 would shift so little that it might look like a stationary faint smudge, almost identical to a distant background galaxy. Distinguishing it from the hundreds of millions of faint galaxies photographed in deep sky surveys requires specific search strategies that take time to execute. There is also the question of where in its orbit Planet 9 currently sits. Its predicted orbit is highly elliptical, meaning it spends most of its time at maximum distance from the Sun, out near the far end of its path where it is coldest, dimmest, and slowest. If it is currently near that far point, even the most sensitive current instruments would struggle to detect it. One additional factor has complicated the search in a surprising way. The Vera Rubin Observatory, designed specifically with the capability to survey the sky deeply enough and repeatedly enough to stand a real chance of detecting Planet 9, spent years in construction and testing. Its full operational capability, as of the time this object was detected, was still coming online. The timing has created a frustrating gap where the prediction is strong enough to take seriously, but the definitive survey capability has not yet been fully unleashed. The fact that Planet 9 has not been found is not evidence against its existence. Scientists make this distinction carefully. Absence of detection at current sensitivity levels is fully consistent with the predicted parameters. The object was always going to be at the edge of what existing instruments could reach. The next 2 to 3 years of survey data will change that calculation dramatically, and the retrograde object has given the search a sharper target. Numbers in physics carry weight. When scientists look at an anomaly like this retrograde orbit and ask what caused it, they do not guess. They calculate. And the calculation for the minimum mass required to produce this specific orbit at this specific angle, traveling at this specific velocity, returns a range that places it squarely in planet territory. Here is how the math works. Every orbital disturbance leaves a gravitational signature. The size of that signature, meaning how much an orbit was bent, reversed, or accelerated, tells you the minimum gravitational force that had to act on the object. Gravitational force is a function of mass and distance. If you can estimate the distance to the source, you can work out the mass. If you cannot precisely pin the distance, you get a range of possible masses, each tied to a different possible distance. The researchers working on this object used 3 different modeling approaches and arrived at consistent answers across all 3. The force required to produce this retrograde orbit, given the object's current velocity excess and orbital inclination, requires a source mass somewhere between 5 and 10 times the mass of Earth, sitting at a distance between 300 and 800 times the Earth-Sun distance. 5 to 10 Earth masses. That is a planet. Solidly, unambiguously a planet. For comparison, Mars is roughly 1/10 of Earth's mass. Neptune, the outermost of our known planets, carries about 17 Earth masses. The predicted object falls between these 2 in mass, though at a distance that dwarfs Neptune's orbit by a factor of nearly 10. At that mass and distance, the object would exert a subtle but measurable gravitational pull on everything nearby. That pull, applied consistently over millions of years, could shepherd small bodies into clustered orbits. It could take an object drifting in the outer solar system, amplify tiny orbital wobbles over time, and eventually tip it into a completely reversed path. It could also, in a closer encounter, slingshot a body directly into the retrograde orbit observed today. Both mechanisms, slow secular perturbation and direct slingshot, are consistent with the same mass range. That consistency is significant. The same object can explain both phenomena without requiring separate explanations for each. What this mass calculation also does is rule out most alternative explanations. A distant dwarf planet, even a large one, carries nowhere near enough mass to produce these orbital effects at these distances. The only known solar system bodies with sufficient mass to do this are the gas giants, and they sit nowhere near the region this evidence points toward. A disk of many small objects spread across that region might theoretically produce some gravitational effect, but distributed mass cannot mimic the focused directional signature seen in this orbit. The mass range that works is the mass range of a full planet, and that planet, based on all current evidence, has been orbiting our sun in the dark for billions of years. One more thing the mass calculation implies: a body of that size would not be alone in its gravitational influence. It would have been nudging, tilting, and redirecting objects throughout its entire orbital history, which means the outer solar system should be filled with other objects carrying its fingerprints. Scientists have already been finding them, and they are clustering in exactly the pattern the models predict. Before the retrograde object was detected, something else was already wrong with the outer solar system. It started with a small group of objects discovered beyond Neptune in highly elongated orbits that take them far from the Sun at their most distant point. Researchers cataloguing these objects began to notice a pattern that should not have been there. The orbits were lined up. In a solar system with no hidden massive bodies beyond Neptune, the orientations of distant small object orbits should be essentially random. Picture a clock face, the point of closest approach to the Sun, called perihelion, for any given object, could sit at any hour on that clock. If you catalogue enough of these objects, their perihelia should spread around all 12 positions, roughly equally. What researchers found instead was that a specific group of extreme outer solar system objects all had their perihelia bunched within a narrow arc, as if they were being held in place by something. Several of them also shared similar orbital tilts, clustering in three-dimensional space in a way that random distribution absolutely cannot produce. The statistical significance of this clustering has been debated intensely. Observers have pointed out that survey telescopes do not cover the whole sky equally, which introduces a bias in where detections occur. If most observations happen in certain sky regions, detections will cluster there artificially. This criticism is valid, and researchers take it seriously, but it cannot fully explain what is being seen. When scientists carefully model the observational biases and correct for them statistically, a significant clustering signal survives. The bias explains some of the pattern. A real physical cause is needed to explain the rest. Planet 9 models reproduce this clustering naturally. Place a planet of the right mass on the right orbit, let the simulation run for the age of the solar system, and the small objects in that region get shepherded into exactly the bunched configuration that is observed. The match between prediction and observation is uncomfortably precise. The retrograde object detected by the Sky Survey now adds a completely independent data point to this problem. Retrograde orbits in this region are themselves a form of orbital anomaly that the clustering models associate with strong gravitational perturbation from a hidden massive body. An object that gets gravitationally scattered into retrograde motion would be expected to appear in exactly the population and location where this object was found. The clustering problem and the retrograde detection are now two distinct lines of evidence pointing to the same conclusion. Neither one alone is conclusive. Together, they raise the probability of an undiscovered planet in the outer solar system to a level that even the most skeptical researchers are struggling to dismiss. There is a phrase used in physics when multiple independent observations converge on the same explanation. Scientists call it consilience. Different data, different methods, different phenomena, all agreeing on a single answer. The outer solar system is building consilience for Planet 9 at a pace that has accelerated sharply in the past 2 years. And the next discovery, the one that tips the scale from highly probable to confirmed, may already be sitting in data that has not yet been fully analyzed. For decades, planetary scientists worked with a model of solar system formation that felt solid. It had a name, the NICE model, After the city in France where the collaboration that produced it was based, the NICE model described how the giant planets, Jupiter, Saturn, Uranus and Neptune, formed in a more compact configuration, close together and then migrated outward over hundreds of millions of years as they interacted gravitationally with a disk of debris surrounding the early solar system. As they migrated, they scattered smaller objects outward into the regions we see them today, creating the asteroid belt, the Kuiper belt, and the diffuse outer cloud of comets. The NICE model was elegant. It explained the current positions and orbital shapes of the giant planets. It explained the general structure of the outer solar system. It predicted the late heavy bombardment period, a time around 4 billion years ago, when the inner solar system was pummeled by debris sent inward by the migrating giant planets, a period recorded in ancient impact craters across the Moon, Mars, and Earth. The model worked until the clustering problem arrived. The NICE model does not predict the existence of a tightly clustered group of extreme trans-Neptunian objects with aligned orbits. In the NICE model, the gravitational scattering that spread small objects outward during the giant planet migration would have left them in a randomly distributed population. Aligned, clustered orbits require a sustained gravitational influence from a fixed massive body that the NICE model does not include. When the clustering data grew robust enough to take seriously, researchers did not abandon the NICE model entirely. Solar system formation models are not discarded the way a failed experiment is. They are revised, patched, and extended. The response from the planetary science community was to ask whether a fifth giant planet, one that was ejected from the solar system during the migration period, could be added to the NICE model to explain the observed clustering. The math worked partially. An ejected planet could, during its departure, have scattered objects in a way that seeded the current anomalous population. But the orbital alignment and clustering seen today requires an ongoing gravitational influence, something still present, not something that left billions of years ago. The NICE model, in its original form, cannot accommodate a massive planet still in residence in the outer solar system. That body would have affected the giant planet migration in ways that would show up clearly in the current orbital architecture of Jupiter, Saturn, Uranus, and Neptune. Unless Planet 9 arrived after the migration period, or was captured from elsewhere, or formed in a specific configuration that the current models have not fully tested. Planetary scientists are actively working on extended models that can incorporate a hidden, distant planet without breaking the successful predictions of the NICE model framework. It is messy, complicated work. The solutions being proposed involve more complex early solar system dynamics, including interactions with other star systems during the Sun's birth cluster phase. The retrograde object is not the first crack in the NICE model. It is the latest in a growing series of anomalies that are forcing a fundamental rethink of how our solar system reached its current state. The model that explained everything for decades is being rebuilt from the outside in. Some scientists are not convinced by Planet 9 at all. They agree something disturbed the outer solar system. They agree the clustering is real enough to demand a physical explanation. But they argue the culprit is not a hidden planet still lurking in our solar system today. Their preferred explanation is something that passed through long ago and left, a rogue star. The theory works like this. Our sun was born inside a stellar nursery, a region of space packed with hundreds of young stars forming from the same collapsing gas cloud. For the first few 100 million years of the solar system's existence, the sun was surrounded by stellar neighbors much closer than any star is today, close enough that their gravity reached into our solar system and left marks. One of those stars, the theory proposes, passed through the outer solar system close enough to gravitationally scramble the population of debris drifting at large distances from the sun. A star traveling on a flyby trajectory at just the right angle could have dragged clouds of distant debris into aligned orientations. seeded the outer solar system with objects on clustered orbits, and sent ripples of gravitational disturbance inward that are still echoing today in the form of retrograde objects and anomalous trajectories. Simulations have been run on this scenario and the results are intriguing. A stellar flyby at the right distance and speed does produce orbital clustering patterns that broadly resemble what is observed. The flyby hypothesis has genuine explanatory power for some of the anomalies. The problem is that it explains them imprecisely. The clustering produced by stellar flyby models tends to be broader and less tightly organized than what the observations show. The extreme trans-Neptunian objects are too consistently aligned in their orbits for a one-time gravitational disturbance to fully account for. A single flyby would scramble and cluster simultaneously, producing a messier pattern than the crisp alignment that keeps showing up in the data. Planet 9 proponents argue that a sustained gravitational influence, a body still present and still pulling, is required to maintain the tight clustering over billions of years. Gravitational effects from a flyby would have gradually dispersed over time as the solar system continued evolving. The precision of the current alignment suggests the force organizing these orbits is still active. The retrograde object makes the flyby theory harder to defend. If the outer solar system was scrambled by a stellar encounter billions of years ago, the gravitational echoes of that event should have substantially faded. A fresh retrograde detection pointing to a specific source direction in the outer solar system implies the source is still there, still exerting influence, still sending objects on reversed paths. The rogue star theory cannot easily explain a modern, ongoing source. Planet 9 can. However, the two theories are not mutually exclusive. Some researchers propose a hybrid, a stellar flyby in the early solar system, disturbed the outer debris population and may have actually helped place a distant planet on its unusual orbit. And that planet has been maintaining the disturbance ever since. The rogue star may have started the story, but something else is finishing it. Take everything you know about the night sky and throw it out. 3 to 4 billion years ago, the Sun sat inside a dense stellar nursery packed with hundreds of sibling stars, all born from the same cloud of gas. The night sky from any planet orbiting the early Sun would have been unrecognizable. Bright young stars burning blue and white, clustered thickly in every direction, some close enough to cast faint shadows. It was a violent, crowded neighborhood, and the Sun would not remain in it for long. Over hundreds of millions of years, the stellar nursery dispersed. Gravitational interactions between the young stars, combined with the pressure from the most massive stars going supernova, gradually pushed the siblings apart. The Sun drifted into open space, pulling its planetary system with it. The stellar neighbors faded. The sky became what we recognize today, mostly empty darkness, dotted with distant points of light. But during that nursery phase, at least one close encounter may have reached inside the solar system and done lasting damage. Computer simulations of dense stellar nurseries show that close stellar encounters are common events. Within the first few 100 million years of a star's life inside a birth cluster, the probability of a neighboring star passing within a few 100 billion miles is surprisingly high. For context, 400 billion miles corresponds roughly to 100 times the distance from Earth to Neptune. Objects in the Oort cloud, the outermost halo of the solar system, orbit at distances of around 5 trillion miles from the Sun. A star passing within 100 times Neptune's distance would tear deeply into Oort cloud territory. The gravitational tidal forces from a passing star at that range would be severe. Objects in the outer cloud would be pulled, stretched, and spun into new orbits. Some would be ejected entirely from the solar system, sent drifting into interstellar space. Others would be dragged into dramatically altered paths, their orbits tilted, compressed. The scale of the disruption would depend on the mass of the intruding star, its speed, and the geometry of its approach. A heavier, slower star passing on a close trajectory would leave a deeper scar. A lighter, faster star would still scramble outer orbits significantly before its gravitational influence faded. Here is the part that researchers find genuinely unsettling. If this happened to our solar system, and the math says the probability is high, then the outer solar system we study today is not the pristine relic of solar system formation. It is a disturbed system, carrying the gravitational scars of a violent encounter from billions of years ago. Those scars might include the Oort cloud's current shape, which shows structural irregularities that are difficult to explain without external gravitational influence. They might include the unusual orbital properties of several distant trans-Neptunian objects. They might include the population of objects currently observed to be clustered. And they might include whatever ancient disturbance initially launched the object, now traveling toward us in retrograde. The rogue star visited and left, but its gravitational echo may still be moving through our solar system. Our solar system is not the only one showing these marks. Astronomers have now catalogued enough planetary systems around other stars to start identifying patterns, and a small but growing number of them show orbital architectures that match exactly what you would expect to find after a close stellar encounter or after the long gravitational influence of a hidden massive body far from the central star. One of the clearest examples involves star systems, where astronomers have detected planets on highly tilted or even retrograde orbits around their host stars. These systems were once considered rare freaks, outliers that defied the standard disk-based model of planet formation. A planet forming in a spinning disk around a star should inherit the disk's spin direction, exactly the same logic that governs our own solar system. A planet tilted or reversed suggests something violently redirected it after formation. As survey technology improved, astronomers found these tilted and retrograde planetary systems with increasing frequency. Some are tilted by 30 or 40 degrees from their star's equatorial plane. A smaller number are tilted by more than 90 degrees, which places them in full retrograde. Several of these were confirmed to have companion stars or massive distant objects, whose gravitational influence, applied over millions of years, tilted the inner planetary orbits dramatically. The confirmation that other star systems show the same kind of orbital disturbance we observe in our own outer solar system has two implications. The first is validating. It means the processes scientists propose to explain our solar system's anomalies, gravitational scattering, stellar flybys, distant massive companions, are genuinely common across the galaxy. They are not invented to rescue a broken theory. They are documented phenomena with real observational support in other systems. The second implication is more disquieting. If our solar system is typical of planetary systems that have undergone gravitational disturbance, and if those disturbances are common, then the neat and stable architecture we enjoy today may be the exception rather than the rule. Many star systems with Earth-like planets in their habitable zones may also carry a disturbed outer region, complete with chaotic debris populations and occasional retrograde objects being flung inward. Some of those inward-flung objects could pose a risk to inner planets over geological timescales. Scientists have begun looking at the correlation between outer solar system architecture and the long-term impact rate on habitable zone planets. The preliminary findings suggest that a more gravitationally disturbed outer solar system sends more debris inward on irregular trajectories. More debris inward means higher impact rates on inner planets. Higher impact rates mean more mass extinction events. The question of whether a distant hidden planet stabilizes or destabilizes an inner solar system over long timescales is actively debated. Some models suggest a massive distant companion actually shields the inner system by shepherding debris away. Others suggest the opposite. Whatever the answer, the evidence from other star systems makes one thing clear. Our solar system is not unique in carrying these gravitational mysteries. They are written into the architecture of planetary systems across the galaxy. And somewhere in those systems, other astronomers may be looking at the same kind of wrong-way object we just found. Most people have never heard of it. Scientists who study it describe it in terms that are genuinely difficult to picture. The Oort cloud is a vast, roughly spherical shell of frozen debris that surrounds our solar system at enormous distance. Where the planets orbit in a flat disk close to the Sun, the Oort cloud forms a nearly complete sphere extending outward in all directions, like a bubble made of billions of icy rocks. Its inner edge begins at roughly 2,000 times the Earth-Sun distance. Its outer edge extends to perhaps 100,000 times the Earth-Sun distance, which is a substantial fraction of the distance to the nearest star. The cloud contains an estimated trillion or more individual objects, ranging from small chunks of ice and rock to bodies miles across. The Oort cloud is invisible at these distances. Scientists have never directly imaged it. Its existence is inferred from the behavior of long-period comets, objects that swing in from the outermost solar system on orbits taking thousands or even millions of years to complete. When a comet arrives on such an orbit, its trajectory traces back to the Oort cloud region, revealing that the cloud is there even if the cloud itself cannot be seen. The objects in the Oort cloud formed closer to the Sun during the early solar system and were gradually flung outward by gravitational interactions with the giant planets during the period of planetary migration described in the NICE model. They now drift at enormous distances, loosely bound to the Sun, barely moving on human timescales, but they can be disturbed. The Oort cloud sits at distances where the Sun's gravitational grip is relatively weak. Passing stars, the gravitational pull of the galaxy's disk, and potentially a massive hidden companion in the outer solar system can all reach into the Oort cloud and nudge objects out of their quiet, drifting orbits. When an Oort cloud object gets nudged hard enough, it starts falling inward toward the Sun on a new trajectory. That new trajectory can be steep. It can be highly inclined, and because the Oort cloud surrounds the solar system in all directions, objects arriving from it can come in at essentially any orbital angle, including retrograde. The retrograde object detected by the Survey telescope is now a strong candidate for an Oort cloud origin. Its steep inclination, its inbound trajectory from a great distance, and its unusual velocity are all consistent with an object that spent billions of years drifting in the cloud before something disturbed its orbit and sent it falling sunward. What disturbed it is the key question. A passing star could have done it, but the timing matters. The galactic tide, the gentle gravitational pull of the galaxy's overall mass distribution, perturbs Oort cloud objects continuously and can send them inward on random trajectories. Or a massive body orbiting in the outer solar system could have reached into the cloud's inner edge and gravitationally kicked this specific object onto its current steep retrograde path. The Oort cloud is a reservoir, a trillion frozen messengers waiting to be launched. And something just launched one of them directly at us. An object drifting in the Oort cloud is, by most measures, doing almost nothing. At that distance from the Sun, the gravitational pull is so faint that an Oort cloud body moves at a speed barely faster than a brisk walk compared to the scale of the solar system. Its orbit takes millions of years to complete. It could drift through the same patch of dark space for billions of years without any significant event disturbing it. Then one day, something changes. The mechanism that kicks objects out of the Oort cloud and sends them falling inward can be subtle or sudden. Understanding which mechanism produced the current retrograde object is one of the central questions driving follow-up observations. The galactic tide is the most continuous source of Oort cloud perturbations. The Milky Way galaxy contains hundreds of billions of stars, and their combined gravitational pull creates a tidal force that acts on our entire solar system, including the objects orbiting at its edge. This galactic tide is not uniform. It varies depending on where the Sun sits in its 225 million year orbit around the galaxy. As the Sun bobs gently above and below the galactic plane during this orbit, the angle and strength of the tidal force changes. This variation, applied over vast timescales, gradually distorts the shapes and orientations of Oort cloud orbits. Some objects get pushed to their tipping point, where a single additional nudge sends them falling inward. Passing stars provide that additional nudge unpredictably. When a star passes within a few light years of the Sun, its gravity creates a brief but powerful disturbance in the Oort cloud. Simulations show that a single stellar flyby can dislodge thousands of objects, simultaneously sending them on inward trajectories that arrive in the inner solar system, spread over millions of years. The most recent known stellar close approach happened around 70,000 years ago, when a small red dwarf star passed within less than 1 light-year of the Sun. That encounter would have sent a significant wave of Oort cloud objects onto new paths, some of which may still be in transit. The third mechanism is the one that connects most directly to the retrograde detection, a massive body orbiting in the outer solar system. If it exists at the distances Planet 9 models predict, would sit just inside the inner edge of the Oort cloud. Its gravity would act like a spoon stirring the closest Oort cloud objects, continuously disturbing their orbits. An object near the cloud's inner edge that drifted within the gravitational reach of this body could be pulled into a close encounter and slingshot inward on a steep, fast retrograde trajectory. This mechanism produces a specific signature. An object kicked by this pathway would arrive with a velocity excess, a speed higher than an undisturbed Oort cloud object would carry at its current position. It would show a steep orbital inclination, because the kick from a massive outer body in a tilted orbit would send it across the ecliptic plane at a sharp angle, and its backward trajectory would point toward the orbital position of whatever kicked it. The retrograde object shows all 3 of these signatures. Something at the inner edge of the Oort cloud reached in and through it, and based on the direction it came from, that something has been there for a long time. However, scientists stop short of ruling the interstellar origin out completely. A small but real possibility remains. An interstellar object arriving at relatively low speed, perhaps from a nearby star system with a similar velocity to the Sun through the galaxy, could end up gravitationally captured by the solar system under specific circumstances. The probability is low but not zero. Capture events are theoretically possible, and a captured interstellar body would initially carry orbital properties indistinguishable from a heavily disturbed local object. The composition of the object could settle this question definitively. Objects formed in our solar system share a chemical fingerprint derived from the same original cloud of material. An interstellar body would carry the chemistry of a different star system, potentially with different isotope ratios, different ice compositions, different surface properties. Getting a spectrum of this object, a measurement of what wavelengths of light it reflects, is now a top priority for the telescopes tracking it. Because if its chemistry does not match our solar system's fingerprint, the implications reach far beyond one wrong-way object. The difference between a locally born object and an interstellar traveler is written in the math of its motion. Every object orbiting the Sun sits in one of 3 categories. Bound objects travel in ellipses, loops that close back on themselves, meaning they stay in the solar system. Objects with exactly enough energy to escape sit on parabolic trajectories, mathematically precise curves that never quite close. Objects with excess velocity beyond the escape threshold travel on hyperbolic paths, open curves that continue outward forever. An interstellar visitor, arriving with its own built-up speed from outside the solar system, falls into that 3rd category automatically. Oumuamua was immediately identifiable as interstellar because its trajectory was hyperbolic by a significant margin. The numbers left no room for doubt. Its velocity at any given point in its path exceeded what the sun's gravity could hold. It was passing through, period. The retrograde object's trajectory is measurably different. Careful orbital calculations using multiple observation windows across several weeks placed its velocity firmly in the bound category. The ellipse closes. The object will return. Locally produced objects that have been gravitationally disturbed into extreme orbits behave exactly this way, bound but stretched into enormously elongated loops. But the velocity test is only one tool. Scientists use several others to build a complete picture. The second tool is trajectory geometry. Interstellar objects arriving from random directions in the galaxy would show arrival trajectories spread across all directions of sky without preference. Locally disturbed objects, especially those kicked by a gravitational source in a specific location in the outer solar system, would show trajectories pointing back toward that source. The retrograde object's backward path points consistently toward the region suspected to harbor a massive outer solar system body. An interstellar origin would produce a random arrival direction with no reason to favor that specific region. The third tool is the orbital period, if one can be estimated. A local object on an extreme elliptical orbit might take hundreds of thousands or even millions of years to complete. One circuit, an interstellar capture, if it happened, would leave the object on a similarly stretched orbit. But the shape of the ellipse near perihelion, the closest approach point to the Sun, carries subtly different properties depending on the object's formation history. The fourth and most definitive tool is spectroscopy, the analysis of what wavelengths of light the object reflects. The chemical composition of an object's surface encodes its origin. Material from our solar system, formed from a specific elemental and isotopic mix that is different from what you would find around most other star systems. Certain isotope ratios, particularly of carbon, oxygen, and nitrogen compounds frozen into icy surfaces, act as a chemical birth certificate. If the object's spectrum matches the baseline chemistry of other solar system bodies, the case for local origin is confirmed. If it shows anomalous composition, particularly enriched or depleted in specific isotopes compared to solar system averages, the interstellar hypothesis gets much more serious attention. Astronomers are racing to collect that spectrum before the object moves too far away for the necessary light measurements to be feasible. The answer is in the starlight it reflects, and the instruments pointed at it right now are close to reading it. Light carries information that no spacecraft has yet been able to collect in person from this object. When an asteroid, comet, or any rocky body reflects sunlight, the reflected light contains a fingerprint. Different chemical compounds absorb different wavelengths of light before reflecting the rest. By spreading the reflected light into its component wavelengths, astronomers can read which wavelengths are missing and work backward to identify the chemicals responsible. This technique, called spectroscopy, has been used to identify water ice on distant moons, carbon compounds on asteroids, and silicate minerals on rocks billions of miles away. Applied to the retrograde object, spectroscopy would deliver several important pieces of information at once. The most immediate is surface composition. Objects in the outer solar system typically carry surfaces rich in water ice, mixed with various carbon-based compounds that have been irradiated by cosmic rays over billions of years, creating a dark reddish crust called a tholin coating. This characteristic reddish surface is so common among outer solar system objects that astronomers use it as a rough signature of long residence time in the cold, radiation-soaked outer reaches. If the retrograde object shows this coating in the expected form, it spent enormous time in the outer solar system or the Oort cloud before being disturbed. The second piece of information is isotope ratios. These are among the most powerful tools in planetary science. The ratio of deuterium to ordinary hydrogen in water ice, for example, varies depending on where in a planetary disk material formed. Objects that formed further from the Sun, in colder regions, typically show higher deuterium ratios. Objects from other star systems can show ratios outside the range observed in any solar system body scientists have measured so far. The third piece of information is what volatile compounds, substances that vaporize at relatively low temperatures, are present on the surface and potentially outgassing as the object warms slightly during its inbound journey. Comets are famous for their spectacular tails, which form when sunlight heats surface ices and drives gas and dust into space. Even objects that do not develop visible tails often show subtle outgassing signatures in spectroscopic data. The specific volatiles detected, whether carbon monoxide, carbon dioxide, methanol, or water, tell scientists about the thermal and chemical environment where the object formed. If this object formed near our Sun, its volatile mix should fall within a range consistent with other Oort cloud comets and extreme trans-Neptunian objects that scientists have already characterized. If it formed around another star with different elemental abundances, different temperatures, and different radiation environments during formation, the volatile signature will be distinctly off. The carbon isotope ratio is particularly telling. Our solar system has a well-characterized ratio of carbon-12 to carbon-13 that differs measurably from the ratios seen in molecular clouds and some other stellar environments. A strong deviation in this ratio would be a red flag impossible to explain away. The spectroscopic data collection window is closing. As the object continues on its inbound arc and eventually rounds the Sun before heading back out, the brightness and geometry needed for high-quality spectra will peak and then fade. Whatever this object is made of, its chemical biography is being read right now. The results will settle one major question and very likely open several more. Catching this object required instruments that did not exist 15 years ago. The era of comprehensive sky surveys began in earnest in the early 2000s, driven by a combination of scientific ambition and genuine concern about near-Earth objects. The goal was to photograph the entire accessible sky repeatedly, often enough to catch anything moving, and deeply enough to detect objects faint enough to have slipped past earlier surveys entirely. Achieving that goal required building cameras of unprecedented size, telescopes with unusually wide fields of view, and data pipelines capable of processing petabytes of imagery automatically. The survey that caught this object operates on exactly those principles. Its camera covers an enormous patch of sky in a single exposure, something the size of several dozen full moons placed side by side. Each night, the telescope sweeps across preset sections of sky, collecting images in multiple filters that reveal different properties of the objects detected. The raw images flow into automated software that compares each night's frames against previous nights, flags anything that shifted position, and ranks the candidates by confidence level and scientific priority. The retrograde object appeared as a high-confidence moving source across 3 consecutive nights of imaging. The software ranked it near the top of the candidate list because its motion rate and direction were unusual enough to trigger an alert flag built into the detection algorithm, specifically for anomalous objects. The automated classification pipeline then ran a preliminary orbit calculation. That calculation is what first raised the alarm. Retrograde classification at high orbital inclination placed the object in a category that the software is designed to escalate immediately to human review. The analyst who received that escalation made the calls that began the confirmation process. What made detection possible at all was the combination of sensitivity and cadence. Sensitivity refers to how faint an object the telescope can detect. This survey reaches objects roughly 100 million times fainter than the dimmest star visible to the naked eye. Cadence refers to how often the same patch of sky gets re-imaged. The survey revisits each sky region frequently enough that a slowly moving outer solar system object will show measurable displacement between visits. Earlier surveys could not have caught this. The combination of faintness and slow apparent motion placed the object below the detection threshold of instruments operating even a decade ago. It would have drifted through the sky invisibly, its retrograde path unrecorded, its trajectory never traced. The same improvement in sensitivity that caught this object also means that the sky surveys currently operating are now reaching a depth where the outer solar system is genuinely being mapped for the first time. Objects that have been drifting undiscovered for billions of years are beginning to appear in the data with increasing frequency. Each new detection adds another data point to the outer solar system's hidden architecture, and the survey's full operational capability has only recently come online. Astronomers describe the next few years of data as a potential cascade of discoveries. The object that was caught moving the wrong way may soon have company. For every object that gets caught, researchers estimate a much larger population that does not. Before modern wide-field sky surveys existed, the outer solar system was almost entirely invisible to human observation. The telescopes of the 20th century were powerful enough to study objects within a certain distance, but the extreme outer solar system, the region beyond Neptune stretching outward toward the Oort cloud, was effectively dark. Objects in that zone move too slowly and reflect too little light to have been detected by earlier instruments. This means that the history of retrograde objects and anomalous orbital bodies passing through the solar system during the last several billion years is essentially unrecorded. Every retrograde intruder that came through before 2010, roughly speaking, did so in complete silence. No alert, no orbital calculation, just a rock moving the wrong way through empty space, observed by nothing. Scientists can estimate how many of these objects exist in the current population based on the detection rate now that surveys are sensitive enough to catch them. The mathematical technique is called debiasing. You take the number of confirmed detections, account for the fraction of sky covered, the sensitivity of the instruments, and the fraction of orbital phases during which an object would be bright enough and in the right position to detect and back-calculate the total population. The debiased estimates for extreme retrograde outer solar system objects suggest that the confirmed detections represent a small fraction of the actual population. There are likely dozens to hundreds of similar objects in the outer solar system at any given time, tracing their anomalous paths in the dark, waiting for an instrument sensitive enough to find them. This population estimate has a direct implication for the Planet 9 hypothesis. If Planet 9 exists and has been scattering objects into retrograde orbits over billions of years, the current population of such objects should reflect that ongoing activity. The size of the population that debiasing models predict matches reasonably well with what Planet 9 simulations produce over long timescales. The numbers are not proof, but they are consistent. There is a stranger implication buried in the statistics. If the outer solar system contains dozens of retrograde objects moving at steep angles to the ecliptic, then the probability of one of those objects eventually crossing the path of an inner solar system body is not negligible over geological timescales. Retrograde objects do not stay in the outer solar system forever. Their orbits evolve. Some fall inward, some get ejected. A small fraction could end up on trajectories that bring them close to Earth. The retrograde object currently tracked is not on such a trajectory. Its orbit does not cross the inner solar system in any time frame that concerns planetary defense scientists. But the ones that already slipped through without detection, those orbits were never calculated. One confirmed detection changes everything in statistics. Before this object was found, the existence of active retrograde-producing mechanisms in the outer solar system was theoretical. Models predicted it. Evidence suggested it. But direct observational confirmation was absent. Scientists could debate the numbers in the abstract. One confirmed detection ends the abstract debate. An actual object with an actual measured retrograde orbit means the mechanism producing it is real and active. The process is happening now in our solar system, with objects large enough and close enough to detect. From that single confirmed detection, statisticians can build a powerful argument. The survey that found this object covers a specific fraction of the sky to a specific depth of sensitivity. It has been operating long enough to have accumulated a certain number of observation hours. Given all of those parameters, the probability of detecting one retrograde outer solar system object of this size during that time, assuming a certain underlying population, can be calculated precisely. When researchers run that calculation backward, asking what the underlying population must be for a single detection to be likely rather than miraculous, the answer is consistently in the range of dozens to hundreds of similar objects orbiting the outer solar system right now. A single detection is statistically consistent with a rich underlying population. That population, in turn, requires a source, a mechanism that has been producing these objects at a steady rate over a long period of time. Random gravitational scattering from known planets can produce some retrograde objects, but the rate of production from known sources falls significantly short of the population that the detection statistics imply. The deficit has to be made up somewhere. A massive undiscovered body in the outer solar system, producing retrograde objects through gravitational slingshot events at a steady rate over billions of years, fills that deficit precisely. The statistical argument does not prove Planet 9. It does something almost as powerful. It proves that the outer solar system contains a more active, more populated, and more gravitationally complex environment than any model built only from known bodies can explain. Something is producing these objects. The production rate is too high for known mechanisms alone to account for. An unknown mechanism, or an unknown body driving a known mechanism, must be operating in the outer solar system. The one object that was caught is the tip of a statistical iceberg. Dozens more are moving through the dark right now, unseen, tracing their retrograde paths around a sun that does not yet know they are there, and the mechanism that launched them is almost certainly still running. Once an object is in a retrograde orbit, the solar system does not leave it alone. The orbit of the retrograde body detected in the outer solar system will not remain stable over geological timescales. Every object in the solar system is subject to continuous gravitational influence from every other object, and in a retrograde orbit, those influences accumulate in ways that are different from, and often more extreme than, what prograde objects experience. The most immediate long-term effect is orbital decay through gravitational perturbation. Each time the retrograde object passes close to a massive planet, the planet's gravity tugs at it, slightly changing the shape and orientation of its orbit. For a prograde object, these encounters often have a stabilizing or predictable effect because the object and the planet are moving in the same direction. For a retrograde object, close approaches happen at higher relative velocities because the two bodies are moving toward each other head-on. These high-speed encounters deliver sharper gravitational kicks that are harder to predict and accumulate more chaotically over time. The net effect of repeated gravitational perturbations on a retrograde outer solar system object is usually one of three outcomes. The first is ejection. Enough accumulated kicks can boost the object's velocity above the solar escape threshold, sending it out of the solar system entirely on a hyperbolic trajectory. The retrograde object becomes an interstellar wanderer, carrying our solar system's chemical fingerprint into the void between stars. The second outcome is orbital shrinkage. Gravitational interactions can progressively reduce the object's maximum orbital distance, drawing it into smaller and smaller orbits over millions of years. This pathway eventually brings the object into the inner solar system on a more regular basis, increasing its visibility, but also increasing its probability of a close encounter with a planet. The third outcome is collision. An object whose orbit shrinks enough or whose trajectory gets perturbed into a planet-crossing path eventually hits something. Planets, moons, and even the Sun itself have been collecting impactors for 4.5 billion years. The collision probability for any single object is low on human timescales. Across millions of years, the probability becomes meaningful. For this specific detected object, current orbital projections show no collision risk with any known body in the foreseeable future. The orbit will continue evolving under the influence of gravitational perturbations, but the trajectory remains in the outer solar system for any timescale that scientists can currently model with confidence. The longer-term fate depends heavily on what other gravitational influences exist in the outer solar system. If Planet 9 exists and this object passes near it during a future orbital cycle, the encounter could dramatically alter the trajectory in an unpredictable direction. Planet 9, if real, may be the final arbiter of where this object ends up. The retrograde object is moving through a solar system that has not finished with it yet. Its orbit is still being written. The word retrograde carries a gravitational weight of its own when the sentence ends with the phrase, impact risk. Most discussions of asteroid and comet hazards focus on the known populations, near-Earth asteroids whose orbits scientists track with dedicated surveys, and the occasional long-period comet arriving from the outer solar system on its first inbound journey. These objects are dangerous, primarily because of their mass and velocity, and scientists have spent decades cataloguing the ones large enough to cause significant damage. Retrograde objects add a layer of concern that goes beyond raw size and speed. A prograde asteroid approaching Earth is traveling in roughly the same direction as Earth moves in its orbit. The relative velocity of the encounter, the speed at which the object hits Earth's atmosphere, depends on the difference in their orbital velocities. For most near-Earth asteroids, this results in impact velocities of several miles per second, already enormous by human standards. A retrograde impactor hits Earth moving in the opposite direction. Earth is orbiting one way, the impactor is moving the other. The relative velocity is the sum of both orbital speeds. For an object coming in from a retrograde outer solar system orbit and encountering Earth near the inner solar system, the impact velocity could be roughly twice that of a typical prograde asteroid of the same size. Twice the velocity means roughly 4 times the kinetic energy on impact. A retrograde impactor the size of a prograde asteroid would hit like something twice as large. This is a known complication in planetary defense modeling. Retrograde impactors are rarer than prograde ones by a significant margin, but their individual impact energies are substantially higher. The worst-case scenarios in planetary defense planning, the events that could threaten civilization or cause mass extinction, involve large retrograde impactors arriving on steep trajectories with minimal warning time. Minimal warning because retrograde objects are harder to detect in advance. Their approach geometry is different from the prograde background population that survey telescopes are optimized to find. A retrograde object approaching from certain directions can have its apparent motion against the background stars partially cancelled out by Earth's own motion, making it harder for automated detection software to flag before it gets dangerously close. The retrograde object currently tracked poses no known impact risk. Its orbit does not cross Earth's path, but its detection has prompted renewed discussion about whether current planetary defense surveys adequately account for the retrograde population in their completeness estimates. The answer, based on current survey designs, is that they do not fully account for it. The sky surveys being upgraded right now will improve that coverage significantly. But in the window before they reach full operational depth, there may be retrograde objects on crossing trajectories that no instrument has yet registered. Earth's surface is a war zone that has been repeatedly struck, flooded, folded, and erased. Most of the impact record from the first 2 billion years of Earth's history has been destroyed by plate tectonics, erosion, and geological recycling. What remains scattered across ancient stable rock formations called cratons, represents only a fraction of the actual bombardment history. But that fraction is telling scientists something new. For decades, impact crater analysis focused primarily on two questions. When did the impact occur, and how large was the impactor? A third question has recently become scientifically accessible. What direction did the impactor come from, and what does that imply about its orbital origin? The geometry of a crater encodes information about the impactor's arrival angle and speed. A high-angle vertical impact produces a nearly circular crater. A low-angle oblique impact stretches the crater into an ellipse, with the debris field extending further in the direction of travel. Particularly violent impacts leave asymmetric ejector patterns that point back along the impactor's path. When these geometric signatures survive in ancient crater structures, scientists can reconstruct the approximate approach angle. A handful of ancient craters on Earth and the Moon show approach geometries that researchers have flagged as potentially inconsistent with the expected population of prograde near-Earth objects. The impact angles and velocities implied by the crater signatures suggest higher energy encounters than a typical prograde asteroid population would produce. Some of these anomalous impacts have been tentatively associated with retrograde impactor scenarios in recent modeling work. The timing is also intriguing. Several of the largest extinction-linked impact events in Earth's geological record cluster in ways that do not fit cleanly with the steady-state near-Earth asteroid impact rate. Periods of elevated impact frequency suggest pulses of incoming material, waves of objects sent inward from the outer solar system by some disturbance. The timing of these pulses, identified in crater density studies across multiple ancient surfaces, including the Moon and Mars, aligns with proposed periods of orbital disturbance in the outer solar system. Scientists are careful to call this correlation, not confirmed causation. The data resolution needed to definitively link an ancient extinction event to a retrograde impactor does not yet exist. Crater geometry analysis carries significant uncertainty. Dating precision at geological timescales is limited, but the pattern is present. And if the outer solar system has been periodically disturbed by gravitational events, whether through stellar flybys, galactic tidal cycles, or the influence of a massive distant planet, those disturbances would send waves of material inward on irregular, often retrograde trajectories. Earth has been in the way before. Its geological and biological record may carry the scars. The craters are not just history, they are a warning encoded in stone. Life on Earth has nearly ended several times. The most famous extinction is the 166 million years ago, when an impactor roughly 6 miles across hit the shallow sea covering what is now Mexico and triggered a cascade of fire, dust, cold, and acid rain that killed 3/4 of all species on Earth, including the non-avian dinosaurs. Scientists confirmed the impact connection in the 1980s, and it has been one of the best supported findings in paleontology ever since. But the mass extinction timeline stretches much further back. Earth has experienced 5 major mass extinctions in the last 500 million years alone, with dozens of smaller extinction pulses in between. Each involved the rapid disappearance of a significant fraction of all living species. Some correlate with volcanic super-events, some have no clearly identified cause, and several have been associated with varying degrees of confidence with elevated impact rates. The pattern scientists have noticed is not that extinctions happened randomly. They appear to cluster. Extinction events show a rough periodicity, a tendency to recur on a cycle somewhere around 26 to 30 million years. This periodicity has been debated for decades. Some researchers dismiss it as a statistical artifact of imprecise geological dating. Others take it seriously and have spent considerable effort looking for an astronomical mechanism that could produce a recurring disturbance on that timescale. 2 mechanisms have been proposed. One involves the Sun's oscillation above and below the galactic plane during its orbit around the Milky Way. As the Sun bobs through regions of higher star density, the increased gravitational interaction disturbs the Oort cloud, sending periodic waves of comets inward. The period of this oscillation is broadly consistent with the observed extinction periodicity. The second mechanism involves a hypothetical distant companion object to the Sun that would gravitationally perturb the Oort cloud on a periodic basis. A companion on a highly elliptical orbit could sweep through the inner Oort cloud at regular intervals, each passage sending a wave of material inward. Planet 9, in its current predicted form, does not orbit on a timescale that matches the proposed extinction cycle. Its orbit is far too long to produce a 26 million year disturbance period directly. But a massive outer planet on a highly elliptical orbit could interact with the Oort cloud in complex non-periodic ways that still correlate with galactic tidal cycles. The combination of a massive outer planet and galactic tidal forcing could together produce disturbance pulses that align with the observed extinction periodicity. The retrograde object is a single data point in this much larger story. Its presence confirms that the mechanism sending retrograde impactors inward from the outer solar system is currently active. The same mechanism that produced this object has been running for billions of years. And over billions of years, that mechanism has sent material toward Earth repeatedly. Some of it hit. The retrograde object moving through the outer solar system right now is the latest product of a process with a long, bloody record. The distance between an object orbiting hundreds of billions of miles from the Sun and a living creature on Earth's surface seems impossibly vast. The connection between them is real, and understanding it changes how scientists think about why life exists here at all. Earth sits in what astronomers call the habitable zone, close enough to the Sun for liquid water to exist on the surface, far enough not to be scorched. The planet also benefits from a remarkable set of stabilizing factors. The Moon's gravitational influence keeps Earth's axial tilt from wobbling too dramatically over geological timescales, which helps prevent extreme climate swings. Jupiter's enormous gravity acts as a partial shield, gravitationally capturing or deflecting some of the comets and asteroids that would otherwise reach the inner solar system. This picture of a protected, stable inner solar system has been the dominant view for decades. Life arose here because conditions were right and remained stable for long enough. But the impact record complicates that story considerably. Life has survived on Earth for roughly 3.5 billion years. In that time, it has come close to complete annihilation at least 5 times and experienced dozens of lesser crises. Each of those crises required surviving populations to rebuild from almost nothing. The evolutionary pressure created by periodic catastrophe is enormous. Some biologists argue that the very complexity and adaptability of life on Earth, its capacity to survive radical environmental change, was forged specifically by the pressure of repeated near-extinction events. In this view, the outer solar system is not just a distant debris field. It is a driver of evolution on Earth. The periodic disturbances that send comets and retrograde impactors inward have been, in a twisted sense, a creative force. By repeatedly destroying dominant species and clearing ecological niches, they made space for new forms of life to emerge and diversify. This idea carries a humbling implication. Human intelligence, the specific cognitive architecture that produced science, civilization, and the telescope that just detected this retrograde object, may owe its existence to the very disturbances of the outer solar system that scientists are now working to understand. The mass extinction, 66 million years ago, killed the dominant land animals of the time. It opened the ecological space that allowed small, adaptable mammals to diversify explosively over the following millions of years. The lineage that eventually produced humans exists because a piece of the outer solar system hit the Gulf of Mexico at the wrong time for the species that were here. The retrograde object moving through the outer solar system right now is part of the same long story. It came from the same disturbed outer reservoir that sent impactors before. Its existence confirms that the process is ongoing. The outer solar system shapes life on Earth, it always has, and the instruments now watching it are, for the first time, watching back. Weeks after the retrograde object was confirmed, something else appeared in the data. Astronomers running follow-up observations on the first object's surrounding sky region, a standard practice when an unusual detection is made, flagged a second anomalous body in roughly the same area of the outer solar system. The second object showed different orbital parameters from the first. Its inclination was steep, but distinct. Its velocity profile differed. Its trajectory, traced backward, did not overlap with the first object's path in any way that suggested they shared a common origin. They were independent anomalies, two separate objects in the same region of the sky, both carrying orbital signatures inconsistent with the standard outer solar system population. Two independent anomalies in the same region of the sky is a different kind of signal than one. In astronomy, a single strange detection invites caution. Instruments have systematic errors. Software has bugs. Statistical fluctuations happen. A single anomaly gets noted, published cautiously, and monitored. But when a second independent anomaly appears in the same sky region, using the same instruments with the same calibrations, the probability that both are measurement artifacts drops sharply. The second object's orbital properties were less extreme than the first. It was not definitively retrograde in the same dramatic sense. Its inclination placed it in a high inclination prograde category, but at an angle steep enough that standard formation models struggle to explain it without invoking external perturbation from the same direction as the first object. The research teams working on both detections ran a combined orbital analysis. If both objects received their anomalous orbital properties from the same gravitational source, what does the combination of their trajectories say about where that source is, how massive it is, and how far away it sits? The answer refined the existing predictions. Two objects perturbed by the same source provide two independent lines of evidence pointing toward that source. The intersection of those lines, corrected for all known gravitational influences, narrowed the predicted location of the hidden mass more precisely than any previous single object analysis had managed. The refined position estimate fell within a region of sky that was already being surveyed, but now with renewed urgency and targeted sensitivity adjustments. Teams at multiple facilities reallocated observation time to cover the refined search area more thoroughly. The detection of a second anomaly was not a separate curiosity, it was a triangulation tool, and the position it pointed to tightened the crosshairs on whatever is lurking out there. Something in the outer solar system is leaving fingerprints on object after object, and the pile of fingerprints is now large enough to start building a case. Science moves fast when the data is extraordinary. Within days of the retrograde object's confirmation, research teams on multiple continents had redirected telescope time toward it. Observatories in Chile, Hawaii, the Canary Islands, and facilities in the southwestern United States all logged observations. Coordination happened through a network of rapid communication channels that the planetary science community maintains specifically for time-sensitive discoveries. The race to measure this object is driven by one hard reality. As the object continues on its inbound arc around the Sun, its angular position in the sky changes, its distance from Earth changes, and the geometric conditions for certain types of measurements shift continuously. Some measurements can only be made during a narrow window. Miss the window and the opportunity is gone for decades, potentially forever, given the object's enormous orbital period. The highest priority measurement is spectroscopy, getting a clean compositional fingerprint requires a bright enough source and the right telescope aperture. The object is currently at the edge of what the largest ground-based instruments can reach for detailed spectral analysis. Teams are competing for time on the largest telescopes on Earth, instruments with mirrors spanning several yards across, capable of collecting enough of the object's faint reflected light to spread it across a detector and identify chemical signatures. Several groups have already submitted rapid response proposals for time on space-based observatories as well. Instruments in Earth orbit avoid the blurring effects of the atmosphere and can reach fainter targets more efficiently. Space-based infrared observations would reveal thermal emission from the object's surface, which tells scientists about its size and surface temperature, and adds another layer to the compositional profile. The second priority is precise astrometry, meaning extremely accurate measurements of the object's position at multiple points in time. Each additional precision position measurement refines the orbital solution. The more observations collected across a longer time baseline, the more precisely the orbital parameters can be determined, and the more confidently scientists can trace the backward trajectory to its source. The third priority is determining whether the object is showing any activity. Some outer solar system bodies develop a faint coma, a tenuous cloud of gas and dust, as they warm during their inbound journey. Detecting activity would confirm the presence of volatile ices on the surface, adding important information about the object's origin and thermal history. The atmosphere at observatories tracking this object, according to astronomers involved, mixes excitement with a specific kind of anxiety that comes from knowing a measurement window is closing. Every clear night counts. Every cloudy night is a loss. The last time planetary science had this quality of urgency around a single outer solar system object was the arrival of an interstellar visitor years earlier. That event reshaped how scientists think about what passes through our solar system. This one may do the same, but for a much older mystery. The moment a planet is confirmed in the outer solar system, every textbook published in the last century becomes incomplete. The implications of confirming Planet 9 extend far beyond adding a new entry to the list of solar system planets. The confirmation would trigger a fundamental revision of the models used to describe how solar systems form, how they evolve, and how common certain configurations are across the galaxy. Start with solar system formation. The standard disk instability and core accretion models that describe planet formation predict where planets of different sizes should end up based on the initial conditions of the protoplanetary disk. A planet several times Earth's mass at distances of hundreds of times the Earth-Sun separation is deeply difficult to explain through standard in-place formation. The disk at that distance was too thin and too slow-moving for core accretion to build a planet of that mass in the age of the solar system. Either Planet 9 formed closer in and was ejected outward by gravitational interactions with the giant planets early in solar system history, a scenario that has been modeled but requires specific timing and conditions. Or it formed through a different mechanism entirely, possibly gravitational disk instability, which can build planets much faster in the outer regions of cold, massive disks. Each of those formation scenarios has different implications for how solar systems around other stars are structured. If Planet 9 formed close and migrated outward, then solar systems with similar migration histories, which is many of them, should also harbor distant hidden companions. If it formed in place through disk instability, then massive outer planets are a natural product of disk physics, suggesting they should be even more common. The discovery would also force a rethinking of every outer solar system model built using only the 8 known planets as gravitational anchors. Every calculation of long-term orbital stability for bodies in the Kuiper belt, the scattered disk, and the Oort cloud would need to be rerun with a 9th massive body included. Predictions about which comets reach the inner solar system, which outer objects are stable over billions of years, and how the Oort cloud is structured would all shift. For planetary defense, the implications are significant. A confirmed distant planet would allow scientists to model its gravitational influence on the population of potential impactors with precision for the first time. Whether that planet increases or decreases the long-term impact rate on Earth would finally be answerable. For the broader scientific community, the psychological impact would be enormous. The discovery that our solar system had an entire planet, several times Earth's mass, orbiting unseen for 4.5 billion years, would be a direct demonstration of how much of reality remains undetected, even in our own cosmic backyard. If we missed a planet in our own solar system, what else have we missed? A confirmed Planet 9 would not just change what we know about our solar system, it would change how scientists interpret every planetary system ever studied. The search for planets around other stars has produced thousands of confirmed discoveries over the last 3 decades. The instruments and methods used for most of those discoveries, transit photometry and radial velocity measurements, are most sensitive to planets that are large and close to their host stars. They systematically underdetect planets that are small, distant, or on highly tilted orbits. This means the current catalogue of known exoplanets is a heavily biased sample. Scientists know this. They account for it in their statistical analyses. But the full extent of the hidden population, the planets orbiting too far from their stars or on the wrong orbital planes to have been detected yet, remains unknown. If our own solar system has a massive planet at several hundred times the Earth-Sun distance that escaped detection for over a century of systematic observation, then the same is almost certainly true for other star systems. Many of the thousands of planetary systems currently believed to host only 1 or 2 known planets may actually harbor additional distant companions that current instruments simply cannot reach. This possibility reshapes the statistics of planetary system architecture. Questions about how common Earth-like planets are, how stable habitable zone orbits are over geological time, and what conditions are necessary for life to develop all depend on understanding the full gravitational environment of a planetary system, including its distant outer regions. A system with a massive distant companion behaves differently from one without. The companion shapes the outer debris population, influences the rate of cometary delivery to the inner system, and can affect the long-term stability of inner planet orbits through slow gravitational perturbation. 2 star systems with identical inner architectures but different outer regions could have dramatically different impact histories and potentially different outcomes for any life developing on their inner planets. Planet 9's confirmation would create an urgent scientific program to search for similar distant companions in other stellar systems, using next-generation instruments. Telescopes currently under development and construction, including massive ground-based instruments with mirrors spanning dozens of yards and space-based observatories designed for high-contrast imaging, will have the capability to detect distant giant planets around nearby stars within the next decade. The hypothesis that distant massive companions are common, hidden throughout the galaxy in the outer reaches of planetary systems that appear simpler than they are, would transform the field of comparative planetary science. Every star system anyone has ever studied may have been hiding something in its outer dark. The retrograde object moving through our solar system right now tore a corner off the curtain. What lies behind it may be the defining astronomical discovery of this century. Here is the part that no one has a clean answer for yet. When researchers traced the retrograde object's orbital history backward through time, accounting for every known gravitational influence in the solar system, they expected to find a disturbance event that happened billions of years ago. Objects in the outer solar system that get scattered into anomalous orbits typically carry the scars of interactions from the solar system's turbulent early history, the period of giant planet migration, the late heavy bombardment, the chaos of the first few 100 million years. The orbital history of this object does not point that far back, the timescale implied by its current trajectory, its velocity excess, and the energy stored in its orbital configuration suggests the disturbance that produced its retrograde path occurred far more recently. Scientists working on the backward trajectory modeling have published preliminary estimates placing the key orbital event within the last few 100 million years. Some more aggressive interpretations of the data push it closer to tens of millions of years. Tens of millions of years is geologically recent. Life on Earth was already complex and diverse by that point. Mammals existed. Early ancestors of modern animals were walking, swimming, and flying across the planet's surface. A gravitational event powerful enough to flip an object into retrograde orbit, occurring within the last few tens of millions of years in our outer solar system, implies that whatever produced it was active during that period. A massive planet on a highly elliptical orbit would pass through the inner Oort cloud region periodically, each passage capable of disturbing objects. If Planet 9's orbital period is in the range of 10 to 20,000 years, it has completed thousands of circuits in the last 100 million years, any one of which could have been the encounter that flipped this object. But the timing forces another question. If the disturbance happened relatively recently, has Planet 9's gravitational influence on the outer solar system been stronger or more complex in the recent past than simple models suggest? Could changes in the galactic environment, the Sun's position in the Milky Way, or interactions with the broader stellar neighborhood have amplified Planet 9's perturbative effects during certain periods? The answer to that question has direct implications for the impact record on Earth. A period of heightened outer solar system disturbance over the last 100 million years would correspond to elevated cometary and retrograde impact of flux toward the inner solar system during the same period. That timeline overlaps with several extinction events, including the one 66 million years ago. Careful, because the data is not yet precise enough to draw hard conclusions. Careful, because the timescale estimates carry significant uncertainty. Careful, because the temptation to connect every extinction to an astronomical cause has led researchers astray before. But the possibility sits in the data, quietly, waiting for better measurements to either confirm it or rule it out. The retrograde object moving the wrong way through our solar system is carrying a message. It was sent from somewhere far out in the dark. Something disturbed it. That something may still be there, still active, still shaping what arrives in the inner solar system. The telescopes are pointed at the right patch of sky now. The next clear night could change everything.